Hey, welcome back. We're talking about inductance in this video. And an inductor is a circuit element that stores energy in a magnetic field. And inductors are very useful. They have applications like in transformers. Suppose you want to step down a voltage from like 120 volts to 100 volts or something like that. You would need a transformer, which is a set of inductors. Or you could step down the current or step up voltage and so on. They are useful inductors, that is, in wireless cell phone chargers. You have your cell phone and you put your cell phone on a brick, a power brick they call those, and then it charges. So in this case, the brick is sensing that your phone is there, and there's some sort of interaction between the brick and your phone that requires no wires. Another application to inductors is in ammeters. Like if you have a circuit, an ammeter is something that measures the current. So if you had a circuit and you put this ammeter over a wire in your circuit, then then it tells you how much current is going through the wire, and this involves the concept of inductance. So let us take a look at how inductors work. Okay, so let's consider first that we have a circuit with some voltage source just to generate some current, and then we have some wire that's been looped many times, hundreds. So the current will be going this way, right? And it returns this way. And then we know we've looked at the magnetic field due to a solenoid before, and we know that right through the solenoid the magnetic field goes like this. Okay, so here's my B field. Okay, and then at the ends it might kind of turn like this. Okay, so that's the magnetic field in a solenoid, and then it comes back around. Okay, that's a really bad drawing, but you get the idea. We've seen this before. So in this circuit, we've got a current I, and that's coming from the voltage source. And we'll say that there are capital N turns of conducting wire. So remember that one turn produces a magnetic field that goes, normal to the loop's surface area vector, or normal to the area, that is. And then if you have n loops that are all kind of stacked closely together, then they approximately just they obey superposition, and they approximately just add to one another. So that makes n times that strength. Okay, so that is to say that maybe the flux due to one loop is B dot ds, like this, due to one loop. And so when you have n loops, then it's reasonable to assume then that all the flux add together. If these loops are all very close together, then they all produce about the same magnetic field and the same magnetic flux. And so we would take n times that, and this is so common to have this solenoid to have loops of current that we actually give this its own name, that quantity its own name. We call that the flux linkage, and we're going to use lambda to represent the flux linkage. Okay, so again, that's just capital N, the number of turns, times the flux due to one turn. Now, as we've shown before, the flux due to one turn is proportional to current I, however much current is going through there. And so, of course, then N times that is the flux linkage, is also proportional to that current. And so we can write the flux linkage like this, where capital L is the constant of proportionality. And so if we rewrite that, we have L is equal to lambda over I, which is, of course, N times the flux divided by I, and we give this the unit of capital H, which is henries, and this L is called inductance. Okay, and inductance is a property of the physical arrangement of the circuit, as you can see, right? I mean, we've got some loops, and we're saying that they're all stacked on top of each other, very close to one another. So it's just a property of the physical arrangement. And as I said at the beginning of this video, an inductive circuit stores energy in its magnetic field. And just to relate this back to what we said about a capacitor's job was to store energy in its electric field. So this inductor is the dual to that device, the capacitor. And we're gonna talk about a couple different inductances. And so this type of inductance, for right now, we're gonna call this the self-inductance. Self-inductance. We're only dealing with one circuit right here. Self-inductance. All right, so you've seen inductors before in circuit analysis course, and you saw it in physics, but you didn't really analyze what was happening too closely inside the circuit. In circuit analysis, you were just analyzing the effect external to the inductor. What effect does it have on the voltage and the current? So if you remember, maybe you remember that the energy stored in an inductor is 1/2 Li squared. Remember, it's the job of the inductor to store energy in its magnetic field, and this is how much energy. You proved that in circuit analysis class, so we're not going to do that here, but it's 1/2 the inductance in Henry times the current going through it squared. Alright, now suppose we had two such circuits. So maybe we have a voltage source there, so current's going to be going this way. Right, and so there's our coil. And then maybe we have a voltage source. Now observe the polarity, so it's down here. So current is going this way. And maybe we have another coil in close proximity. Remember that the inductance is a property of the physical the physical arrangement of the circuit. Okay, so now in this case we've got two magnetic fields happening here. The current in the one on the left, the circuit on the left, goes this way, and so the magnetic field is going to let's say go like this, and it's going to pass through that solenoid as well. So there's going to be a magnetic field and with magnetic flux from circuit 1, which is the left circuit, through circuit 2, and we'll represent that psi 1, 2. Right? And then there's also kind of flux lines that do not go through circuit 2, so maybe this is just psi 1, 1. Right? And similarly, from circuit 2, there's going to be flux through circuit 1. And because I've flipped the battery, the voltage source, it's going to go in the same direction like this. We'll call that psi 2, 1. And then this guy is going to go like this. We'll call that psi 2, 2. That flux due to circuit 2 does not pass through circuit 1. And so you see there's a magnetic interaction that's existing between these two circuits. So my notation here is that psi I j, we don't have to stop at two circuits, but so I'll just say psi I j is the flux through circuit I due to circuit J. So I may have misspoke before. So this one here, this would be the flux through this circuit 1 due to this guy over here. And you'll see psi 2, 2 then is the flux through circuit 2 due to circuit 2. So that's the self-inductance. Okay, so we can express psi ij like this. We can say that this is an integral then. We're going to integrate over the surface of the ith circuit. So So for circuit 1, right, the flux through circuit 1, so that would be this guy's surface area, right, of each coil. And then what are we going to integrate? We're going to integrate the magnetic flux density due to circuit 2 or circuit J. Right? And so that's how we come up with psi ij. Now, similar to what we said up here with inductance, I can define what's called the mutual inductance. Right, so remember we talked about self-inductance up here. So mutual inductance, I'm going to call mutual inductance Mij, and it's the ratio of flux linkage, we'll say lambda ij, which would be Ni times psi ij. So this is the flux linkage on circuit I to current J now. On circuit I to current J. Okay, so we can express the mutual inductance like this. Mij is the flux linkage. So I'm missing the ratio right here. The ratio of flux linkage. So this is the ratio of flux linkage on circuit I, and then to current J, right? That ratio. So we can write this as N capital I lambda psi ij over ij, like this. Okay, so now we've got this idea of mutual inductance, and remember that the idea of inductors is to store energy in a magnetic field. Now let us modify the definition of self-inductance. So now let's say Li, so the inductance of the ith circuit. So now we're coming back to self-inductance. So that's its own flux linkage then, divided by its own current. Right, so this would be Ni lambda psi I divided by I sub I. And here we're letting psi I, this is the total flux. So this is the flux due to circuit J plus the flux due to its own circuit. All right, now the total energy then in the magnetic field, in this magnetic field then, is, remember we've got it's the job of the inductor to store energy, and so we have three inductances basically. We have the mutual inductance, right, and then we have the self-inductance of both circuits. So this is 1/2 L1 I1 squared plus 1/2 L2 I2 squared, and then we'll do a plus or minus the mutual inductance, so that's playing the role of L, the mutual inductance, times I1 I2, and we're going to choose the plus if the magnetic fields align in the same direction, like I have drawn. Psi 2,1 and psi 1,2 are in the same direction, so we would use plus in this case. The energy adds together, right? Same direction. and then we would use minus if psi 1 2 and psi 2 1 are in opposite direction. They're taking away from one another. Okay. So you can see, actually before I erase this drawing, at the beginning of this video I said there are applications in transformers, wireless chargers, and ammeters. Actually, it doesn't stop there. In traffic lights, you use inductors to sense that a car is at a light. So there's a lot of sensing applications for inductors. So you can see why that is. So for transformers, let's take wireless chargers. So this might be the wall outlet here, and so you plug so this circuit is actually the charging brick. So you've got your charging brick plugged into the wall outlet, so there's how you get power, and then the charging brick has a big coil in it, and that's giving off a magnetic field. Then you put your phone, which is the second circuit, on top of that brick, right? And so your phone has a battery, right? And so then the energy in the magnetic field from the brick goes into some sort of inductor in your phone, and then that creates a current that charges so that takes the energy in the form of a current that charges the battery. Transformer, you have two circuits, and so you would have a high voltage if you wanted to step down right here, and then you can use the mutual inductance idea to step down and make a smaller voltage in a transformer. And an ammeter is similar. You have some circuit here, and you want to measure the current through that circuit. So you have an ammeter which has an inductor, and you put your ammeter close to the circuit, and it measures the magnetic field, and from that magnetic field it can deduce what's the current going through the wire. Alright, now in the next couple of videos we're going to work on calculating the inductance of an object. And so I just want to kind of point out the process to you. It's a very similar process as we used to find capacitance. Again, the faster you can see this dual nature between magnetism and electric fields, the better. So again, the inductor is the dual to the capacitor. So if you remember how we calculated capacitance, then you'll be good here for finding inductance. So what we're going to do to find the inductance of an object is we're going to choose a coordinate system, right? So if we're looking at a coaxial cable, then of course we would want to choose cylindrical coordinates, for example. And then we're going to let the inductor, or assume the current to be I. Okay, maybe you recall the process for capacitance. We did something similar. Then we're going to find B, right, due to the current that we just assumed, and we can find B with, for example, the Biot-Savart law, or Ampere's law, and then we can calculate the flux. The flux is the surface integral of B dot ds. So we find the flux, and then to find the inductance we take N times the flux divided by I. Now I will be, remember we said that the flux will be proportional to I, so there will be an I implicit in this psi up here, and so I divided by I will drop out. The I will drop out, and that's good because we assumed it up here. Alright, so again, I think I've got a couple videos coming up on the calculating the inductance of some arrangements. So let's take a look at those.